So in the completion, we need to make 4 major decisions. One is the bottom hole completion. How we connect the reservoir to the wellbore. That is called bottom hole completion. Yeah. Hole completion. Selection of production conduit. You know, when we decided how to connect the well to the reservoir, then how we are going to bring the fluid to surface. That's called production conduit. Now, which facility we want to put in the well? For example, do you want to protect the casing? Do you need extra energy? Do you need to do gas lift? Do you need to put a pump downhole? This is called production stream facility. And then this one is component. What component we put there? Because for each activity, there are different components. For example, if you want to kill the well, there are various options. We can have a sliding side door. We can have pressure valve. We can have punching the tubing. There are various options. So which one we choose? And then uncertainty and alternative design. So first, start from a flat surface, okay? We use a 28 to, first we put a conductor pipe.
Excuse me, sir. If you are not sharing your screen, it's we just see you, not the slides.
Oh, you don't see the slides?
No, because you started recording and it...
I can see the slides. I can see the slides, Piro.
Really? I don't see them.
I can see the slides, Piro.
Everybody can see the slide?
Yes, yes, yes.
Yeah, I guess it's just me.
Why you cannot see? What you see?
Okay, I fixed it. Okay, I fixed it. I had to press to switch. Okay.
Okay. So first, this conductor pipe. It is normally 30-inch pipe to the depth of around 30 meters. Yeah, more or less. The reason we put this conductor pipe, can you guess what is the reason? The reason is that once we are drilling, we have a heavy rig at the top here, okay? If you are drilling, if you don't have the conductor pipe, it will excavate, yeah, underground. Because that water that we are using for drilling and make a big cavity here. And then the rig will collapse, okay? So it make a big cavity here and the rig will collapse. So that conductor pipe protect the shallow sediment. And then once they run the conductor pipe, now the system is available for further operation. After that, the drilling rig will come to the site. And first with cement, we make a space and protect this area, and then the rig comes in. Once the rig comes to the site, then first we use a large drill bit, 23-inch to 27-inch, and drill and go down. This will go inside this 30-inch pipe. So when we reach the desired depth, what is the desired depth? It is a depth that bypass drinking water, aquifer. Yeah? Because here the initial drilling is water, with normal water, that it doesn't damage, it doesn't pollute the aquifer, shallow water, okay? And then we run this 18.5-inch casing. Then we cement it. For cementing, this graphic may not show the real shape. For cementing, we inject cement from inside the well and recover it from surface. Yeah? And then from surface. Now, what is we are doing cementing? Cement is an important task in drilling. Because if it's not a good cement, we have many problems with that well. So we install the 18.5-inch, 85/8 casing. Then we put what we call it blowout preventer on top of this casing. Now this is because in shallow water the pressure is hydrostatic pressure, and the pressure is basically zero because they are all connected to each other, and we don't have any problem here. And then we go for the next section and 17 and 17.5 bit for drilling, and then go to next section. The next section is 13.38, and we run this casing and cement it. Okay? And then we go with, so this will end up normally to the top of reservoir. Yeah? So this is aquifer. This is high pressure or low pressure water, but it's not aquifer. And this is top of the reservoir normally. Then we enter the well with 12.5 quarter bit and drill and cement it. Now this is the reservoir section. Yeah, this is when we drill it. Before cementing, we run a lot of logs to see that how much oil we have, how much gas we have, you know. And then sometimes it's necessary to drill more, then we can run deeper and 8.5 bit, and then run the what is called liner. The difference between liner and casing is that casing is cemented to surface, but liner, no. Okay. So that is in at the downhole. Yeah. Bottomhole completion is that how we connect, because they're all cemented, yeah, how we connect these to the reservoir. Reservoir is here. Okay. So what happened on the surface? This is 1858. This conductor pipe is here. Conductor pipe is here. They normally a little bit on the surface. We drill and we put 1858. And then we put the base flange. Yeah. And we put the BOP on top of this base flange here. Yeah, I discuss what is the BOP. We put it here. And then we drill. Now we can use mud. Here, initially, all water. And we drill, go to the next steps, and then run the casing. Yeah, you see that the casing 1338. The red one is 1338. Is you see that is hang here. Yeah, and there is a side valve, 2-inch side valve here that measure the pressure between these two casings. Is double valve, 2-inch double valve that we find if you want to production engineer when they go to site, they measure pressure here and the fluid that comes out because it can indicate problem with cement, corrosion, you know, and you can observe that. The next one, you run the next flange, you drill and run the next flange, and then this is 958. Yeah. The blue one is not 958. The next case. Okay, and we put another casing head, and we run 958, and then we run the tubing and hang it here. So now we have 3 valves here. You see that this is one, this is another one, and this is another one. This is called Annulus A. This is called Annulus B. And this is called Annulus C. From C, we measure the pressure between 1858 and 1338. From B, we measure pressure between 1338 and 958. And A, we measure the pressure between tubing and casing, 958. Yeah. Normally, the problem is annulus A, because it's directly connected to high pressure fluid. B is less dangerous, C is less dangerous. So, how to do the bottom hole completion? One option is called open hole completion. It means that this is top of reservoir, this is top of reservoir, this is 958. Yeah, or 1338, depend on what plan they have, and then the rest is open hole. Means that there is no casing. The benefit here is that no perforation. You save the cost of cementing, logging, because if you cement it, you need to know which part you need to connect. So that's why you need to do logging and log interpretation. Logging is devices run on a logging tool and measure the porosity, measure the amount of oil, amount of gas, amount of water, some extra tests which show you permeability. If you don't need these measurements, for save time, less time, you pay less money. The other point is that full diameter is available. But the problem is that there is no flexibility, no selectivity for production. You cannot say how much I want to produce from here or how much I want to produce from somewhere else. Yeah, you cannot decide where to produce, okay? So here you have gas, you might produce gas. Here you have oil, and here you have water, so you might produce water, okay? So you don't have selectivity. Another option is to use an screen. That is to some extent reduce the chances of sand production. Because as you produce, the sand can be produced, and sand is dangerous because it can cause erosion. Any place you have a bend, change in direction, sand can cause erosion and cause problem. So this perforation, this slotted liner will to some extent prevent sand production. But if you notice, there is a gap between here and here. That will mobilize sand. because the sand can move in. And when it moves in, then a small particle will cut away this screen, and then big particle. So we need to minimize sand movement. So there are two major options how to prevent sand movement. One is that to inject sand, a special size sand, behind the screen to prevent sand movement. That is called gravel pack. So that's one option. The problem with gravel pack is that it creates extra resistance. The other option is that to move the screen to touch the formation. That is called expandable screen. So the screen with special devices, you push them back and then will touch the surface of the sand and then doesn't move. Okay? So these are the two major options. But the weak point of this is that, again, you don't have selectivity. If the water is produced here, you cannot prevent it. If the gas produced here, you cannot prevent it. Okay? The most popular option is that cement the casing and then connect to the zone that we are interested by perforation, by making hole in the casing. Therefore, you definitely need to run lugs because you need to know where to perforate. You don't want to perforate in shave zone. Yeah, you want to perforate in high permeability and high oil saturation, high porosity section, because that will produce more oil fall. Now, there are two costs here. One, the cost of the logging and log interpretation. Two, the cost of rig, because the rig of drilling rig needs to wait there for this logging to finish and then run the casing. And rig can be very expensive. Offshore, at the time that oil was $148 per barrel, you know, you can have rigs that cost you $500,000 per day. So you can see that it is a very expensive process. But it gives you option, controlling where you want to have flow or where to block, you know, that option, that's the benefit of these options. Now, so how we choose, okay, that was bottom hole completion. The next step is that to decide how to bring reservoir fluid to surface. Okay? So these are the parameters which are important in choosing the completion. Cost, flow stability, that's an important issue. Ability to control flow and safety. So the question here, is there any, I don't know if there is any problem. Okay, no problem. Okay, the question here is that how to bring, we finish this part, how to bring this fluid to surface, is production conduit. And there are various options. Tubingless casing flow, casing and tubing flow, tubing flow without annular isolation. I have seen casing flow without annular isolation, but the most popular is this one. And I explain these options. The first one, casing flow. Casing flow is good for high permeability reservoir and high rate. So, because there are 3 elements in pressure drop to surface. One is hydrostatic head, because you have the fluid here. That fluid has the density, therefore is hydrostatic head. One is friction. Friction depends on velocity. Friction, pressure drop, depend on velocity. Hydrostatic depend on the density of the fluid here. But friction is a function of fluid here. But friction is a function of the velocity. Another element is kinetic energy, because here the fluid is under pressure, the volume is small. Here the pressure has been reduced because of pressure drop, and the volume is much larger, because some gas will come out of the oil, and then the volume is larger. So here velocity is low because volume is less. Here velocity is high. Change in velocity will happen. It takes a time from here to move. So change in velocity versus over time become acceleration. And then it is a mass is moving, acceleration multiplied by mass become force. So M force equal to mass delta V divided by delta T. Okay, velocity changes, It takes the time for the fluid to move, so there is a change in velocity. The fluid has a mass that becomes force. And then force multiplied by distance become work. Okay? So some energy converted to acceleration, it takes, but it's normally very small. So here you can see that the diameter is big. So the good point with a larger diameter, velocity would be low. Therefore, friction pressure drop is low, is good for high flow rate wells. Yeah. But the problem is that low velocity will cause fluid segregation. You see that we are producing oil and gas. As they come to the wellbore, yeah, and if the oil and gas come here, as they move up, pressure drop, more gas will come out. As move up, more gas will come out. Gas can move faster. So the oil will remain behind. That will result in what is called holdup. Liquid holdup. Therefore, the column become heavy. And that's heavy the column becoming heavy. Do you remember I said that hydrostatic head depend on the density. So therefore, the density increases, and that will result in flow segregation and increase in hydrostatic head. So it is not good for low flow rate. The other issue is that the casing is exposed to high pressure. You know, casing is a large diameter pipe. And if it's high pressure, normally the casing have lower pressure rating, around 3,000 or 5,000, something like that, PSI. So exposure to high pressure can result in casing to burst. And if you think about it, see, so here, if it is the casing, you have a pressure here. So pressure multiplied by internal area of the casing is force. Okay? You cannot change the pressure, but you can change area. That's why high pressure lines are very small. So if you exert high pressure to casing, the casing can burst. And the only way the casing can prevent or protect the casing is to make thicker casing or a higher grade. Both of them will cost money. That's why we run tubing, because tubing is smaller diameter. So we have a limitation on how much pressure we can put in casing. And also because reservoir fluid can be corrosive and erosive, erosion, because high velocity fluid movement can cause erosion. And if you have saline water, you have H2S, CO2, that can cause corrosion. The other point is that how to kill the well. Yeah, how to kill the well. If you want to do some repair, you need to kill the well. And normally we have to replace this column with heavy mud. Yeah, this column, we need to fill it with heavy mud. And you cannot inject normally bullheading, what is called bullheading, that you force the fluid to the formation. It's very difficult because you might have some solid particle coming out and then they don't want to go in. So sometimes we need to run tubing to what we call it cold tubing to replace it. So one option is squeezing, what is called bullheading. Another one is volumetric. That is, you inject some mud and wait for the mud to settle down and then remove the pressure and then inject more mud and then reduce pressure, inject more mud, and gradually fill up the well, the conduit. And then another problem, how to revive the well. When you finish your job, how do you revive it? Yeah, how to make the well to flow. You cannot knee and say that, you know, go to on your knee, say that please flow. No. So you need to replace this heavy mud with light fluid. Here you have swabbing, you can put a device inside and pull the fluid out, or you can run cold tubing and inject nitrogen to move the heavy mud outside and the well is starting to flow. So you see that there are many limitations here. Another option is that casing and tubing flow. That will address some of the difficulty of tubingless. Here you see that the flow rate would be more or less the same, but you have the option to kill the well. You can inject mud from here and replace the oil and produce from here, or the other way around. Yeah. So ease of circulation, and when the repair workover is finished, you can inject light fluid, and replace it with heavy mud. Sometimes they use it as a gas lift. So they inject gas from here, and it comes to the bottom, and then reduce the density of the fluid here, and therefore the well can start flowing. Now, This is good for high flow rate, but you have also this problem of corrosion and erosion in the casing. You want to always to protect casing because you can remove tubing, you can remove it, but casing is fixed. You cannot remove the casing. So to protect the casing, and especially for low flow rate wells, you can run tubing, but don't put a packet. So to some extent, you protect the annulus, the casing, and it is easy to start the flow, to kick off circulation. You can also use as a gas lift. The problem here is that when the reservoir fluid is produced, okay, come here. So it is gas and oil. Gas and oil can go this way. Can you see my picture, the presentation?
Yes, Professor, we can.
What is happening here? Okay, so oil and gas is being produced here. They come here, and oil and gas goes here and here. And the gas will separate at the top. Yeah, gas will separate. And the next oil and gas, more gas, more gas, more gas, yeah? So it will fill all up to here gradually. Now, the first problem is that because gas density is lower, the pressure here will be high. So high pressure in the annulus, high pressure in the annulus. That's one problem. Because, you know, as we move down, the pressure increases. As we move up, the pressure is reduced, okay? So now you have the reservoir pressure here is fixed during production, so we know this. The pressure here it's driving me mad. So let me do this from here. You see that the pressure, the fluid come here, and the gas oil and gas goes here and here. Here is produced, but here is not produced. So therefore, the gas will accumulate, and then the pressure here, reservoir pressure, the pressure here as we move up, the pressure will be reduced, okay? And that is a function of the density. So here is, for example, 3000 psi. Here is 3000. And then density of the gas is 0.1 psi per foot. The depth of the reservoir assumed is 10,000 feet. Yeah. So the pressure reduction, if the column is gas, pressure reduction would be 1000 psi. So pressure here would be 2000. Here, 2000. It's high pressure. What about this section? Here you have oil and gas, assume a density of 0.3 or 0.225 per foot, because density of oil is 0.35, density of the gas is 0.1. So this is 2.5, and then 3,000, 10,000 PS depth become 2,500 hydrostatic head. And we have also frictional pressure drop, and the pressure at the surface could be 500. So you see that the annulus, the pressure would be very high, and that is dangerous. Okay, and also when the gas fill in, then the gas will go into the tubing. As it goes to the tubing, the pressure will be reduced, and more gas will come. So the system becomes unstable. This is called annulus heading. This is called annulus heading. And that's previous one, casing exposure to high pressure. As I said, I've seen places that they use annulus as flow conduit, but it's not recommended because you will cause corrosion and erosion. The best option is this one, annulus tubing flow with Annulus Isolation. So we separate this section. So we protect the casing, and the fluid is going through tubing. Okay? So you might say, okay, how do I kill the well? You can put some, what is called a sliding side door. Okay? And because the space for gas collection is very small and the pressure is high, so we don't have annulus heading. The only point is that to balance the pressure across the packer, because here is reservoir pressure, and here you need to put some fluid here to counteract this pressure, because otherwise the packer would be unset. And it causes problem. So this is by far the most popular competition. The completion string facility, they can be divided in two sections, essential or non-essential. And normally in the industry, they said, keep it simple. Yes. Okay. Because if you make it more complex, there is more chance of failure. And the failure is very expensive. So essential is pressure and flow containment, annular isolation, downhole corrosion, closure, circulation, and tubing isolation. These are the main components. And here you can see these main components. The pressure and flow are contained in production casing. This is production casing. Yeah. Production tubing. This is the tubing. Can you see my cursor, I assume? Yeah. Or I can go to pointer.
We can, Professor. Yes.
Yeah. You see that this is the tubing. Wellhead. This is what is called wellhead. And this is Christmas tree. And the packet. This is the packet. So this is the minimum. Yeah. Okay. Now, annulus isolation is very important. As I said, the most popular technique is to tubing with annular isolation. In production wells, because there are three types of wells, or maybe four. One is production. Two is observation well. What is observation? Because when we produce, we want to know how much the level of oil and gas has changed and pressure in the boundary of the reservoir. Then injection well. For pressure maintenance or EOR or whatever, we need injection wells to inject oil or inject gas or water for secondary recovery. The other one is disposal. Sometimes some water produced or cutting during drilling are injected in disposal well. There are other options as well, you know, like controlling. If you have a well blowout, then you can have relief valve, wells. But production well, we put the packet to prevent annulus heading and also to prevent corrosion and erosion to the casing. Injection wells, if you are injecting water, here injection pressure is high, and if you don't want to inject high pressure into the well, damaging the casing, so this is protecting the casing against high pressure. So as I said, tubing has less surface, internal surface. Therefore, the pressure and the force on tubing would be smaller because force is pressure multiplied by area. So for injection well, it's always recommended to have a packet, a tubing and packet. And how we, what is the packer? How does it work? Packer has two main elements. One is something that will mechanically attach the packer to the tubing and to casing, yeah, to casing. This is the packer. It's above here is the tubing. This is the casing. And this is mechanical means to, when we want to set the packer, we put downward force or we squeeze the packer, and this locks, they go over this conical surface and set the packer. Now the packer mechanically cannot move upward. It can move downward, because if it's moved downward, then this slips will come out, and then it can unseat the packer. The other, and then when we secure mechanically the packer, that now this is elastomer. Okay, we were talking about packer and its role. So this is the tubing is here. This is tubing. So tubing is attached at the top here. Yeah. Tubing is attached here. This is the casing. Now you put a centralizer to to center the packer, and then when you reach to the depths, mechanically you fix it by putting the pressure or rotation or squeezing the two ends to this slip to go over this slope, yeah? And then they will be locked here. And the same with this. And then after setting the packer, this elastomer will expand. In fact, the pressure will cause the elastomer to expand, and they will provide hydraulic sealing. This packer is called a tension packer. Why? Because it needs to be under tension. So this is called tension packer. So it prevents movement upward, but it doesn't prevent movement downward. So we can have compression packer as well. Or we can have a packer which has tension and compression together. So that is a fixed packer. Here, this is a slip here, if you can see. Yeah, they are the tension. So this prevents upward movement. here, this is slip here, they prevent downward movement. So it's a tension compression packet, and then elastomer will expand to seal. This is another tension packet. Yeah. We also need circulation capability because we want to, might be necessary to kill the well. We discussed about squeezing and volumetry earlier. So we discussed that. We discussed cold tubing and snubbing unit. Discuss that. We can also create port between tubing and annulus. There are three main options. One is a sliding side door or side sleeve, side pocket mandrel, and ported nipple. I try to explain them. If we don't have these, normally killing the well is necessary. We want to do a major repair. Therefore, we need to change the tubing. So one option is that to punch the tubing and establish the circulation and killing the well. So this is the sliding side door. There are two tubes inside each other, and when they are in direction, here you see that the flow can come out, but you can move it with wire line that I'll explain later. And now the port is closed. Yeah, the fluid cannot move. Another option is side pocket mandrel. There is off-center sort of cavity here that we can put valves here or remove the valve, and that will create circulation between tubing and annulus. So the other ported nipple is something similar to this. You put port between them and you can have circulation. The other facility that we put in the tubing is tubing isolation. This is in addition to subsurface safety valve. So subsurface safety valve. This is a device that can close the well from inside and become very popular after Iraq attacking Kuwait. Because normally for oil wells, we didn't have subsurface safety valve. We had subsurface safety valve for gas well, offshore wells, and well in the border region. Just in case there is a sabotage or terrorist attack. So the tubing isolation can provide facility that we can put a plug inside and therefore close the tubing. Normally, it is provided at the very end of the tubing. And we use a wire line plug to open it or close it. It has several applications. It can work as a safety, one safety factor for any operation in oil and gas industry. We need to have two safety factors. So it can work as a safety factor. Also, it is used for pressure testing. When we are running the tubing comes at the length of 10 meters and connected to each other. And to make sure there is no leakage, we used to run a plug and the tubing isolation, and then put pressure and see that if there is any leakage. Normally, after 5 to 10 tubing lengths, we used to do this test. These days, they can do the same test outside. So that application may not be valid these days. Remember this figure. This figure has been in the exam several times. This is the basic well completion schematic. So this is from reservoir, from here. This is the tubing isolation plug that can work as a safety factor as a safety factor for any process. It can be used for pressure testing. And then we have the annular isolation. Yeah, annular isolation packet. Then we have circulation, a sliding side door. That is, remember, for circulation between tubing and annulus for killing the valve. Then we have subsurface safety valve. And this is the production. This is from annulus. This is from tube. Please remember, these are the essential, the basic well completion. There are many non-essential. Tubing detachment, because normally any tubing problem will happen above the packet. So this will give us opportunity to pull out the tubing without touching the packet, because packet is expensive, and if we don't need to pull it out, then we shouldn't pull it out. The other one is tubing stresses, because when we are producing hot fluid from bottom of the valve comes to the tubing. So the tubing will, length of tubing will increase. And because tubing is fixed at 2 points, at the wellhead and the packet, that can damage the tube. So we have devices like telescope-like devices that the pipe moves inside the shutter and take care of the stresses. And sometimes we want to have monitoring devices. So that is an option. And inject the fluid into the tubing, control injection of tubing. For example, we want to inject, I don't know, gas lift or downhole pump system. And then another one is wire line entry guide. So here you can see this element. The wire line entry guide, if you have run the wire line, when you are pulling out, it must get stuck on the edge of the tubing, and that will cut the wire line wire, and then that would be very difficult to recover it, and it costs a lot of money. The next one is a pressure and temperature monitoring devices. So you put it here. If you can recover this, and then there is a recorder in the memory, and you can read pressure and temperature for a month or a year. You know, the data is there. But when you monitor, put it pressure and temperature devices here, they prevent flow, or they cause a partial blockage. Then we have a perforated flow tube that the flow can come from bottom here and then come through this flow tube. Move on. And then this is the pressure isolation, tubing isolation valve. Here we put a plug and can be, as I said, as another safety factor. And this is what is called mill-out extension. Mill-out extension, you see that the diameter is larger than tubing diameter. When we have permanent packet, we have two types of packet, non-permanent or permanent. Permanent is cheaper and more reliable. But if you need to pull it out, you need to have a milling system to go down and cut the packet to prevent the packet to fall inside. We put a cache sleeve that needs more space to open up, and then you pull the packet. So that's why mill-out extension. And in this anchor, this is when you, as I said, sometimes you just need to take the packet, the tubing out, not the packet. So we have seal assembly, and we can pull it out the tubing side. And then there is another location for having a plug. This is a sliding side door, yeah, that creates flow between tubing and annulus. This is subsurface safety valve, yeah. You see that there is a pressure line to open or close subsurface safety. So it's a basic design from one zone production. So we are producing from one zone. Yeah. Now here, when we need a pump, you see that normally the motor is below the pump because all the energy we give to the motor will not be converted to mechanical energy. So there is some heat generator because the system is not perfect. That heat creating the motor can be used for heating up the fluid, therefore reducing the viscosity and density of the fluid. So it will help the fluid to be pumped. If it was the other way around, if the level of fluid was below this section, then the pump would have burned. And also it wouldn't help in pumping the fluid. So here, the motor is always below the pump itself. And that motor is powered by this power line. Yeah? And there is a junction box and surface. And then normally we have a very variable speed system here that when we start the pump, we don't put full power. Initially, we put less power to prevent burning because you're just starting the pump, it needs a lot of energy. And then you can increase the RPM and the power. But then comes here and come to the production, the tubing, and goes to production, okay? But here, you see that is continuing down here because for this case, we want to have access to below the pump. Because if we have the pump here, we cannot run something or a wire line through this line. So we have a sort of Y-top connection that we can produce the fluid from bypass pump. If we need to do wire line, so we have this case open, we can do wire line. Here it is called a Y-tool block, and it has, when there is a sort of door here, a valve here, that when the well is producing, this part is closed. And when we stop production, this part will open and we can do wire.